All right, so the review sheet on chapter 1, I have about 8 questions on chapter 1. Most of them have to do with the vocabulary words in chapter 1. Okay, I'll tell you that right now. Now, you will not get a test bank, a word bank, so you think about some of the words that were in there. Maybe observation is one of them. Maybe hypothesis would be another one. I noticed that last year, some people on your notes, some of you wrote scientific theory, but you didn't write scientific law. That was in that too. What's the difference? A scientific theory, you have to have an actual set of experiments that all point to the same idea before you can have a scientific theory. But what's a scientific law? Like the law of gravity. What's that? Well, that's just explaining a behavior, isn't it? We don't really have a whole bunch of experiments proving gravity. We don't have that. So that was the difference there. So as far as this, I would say just be ready to have mostly vocabulary words for chapter 1. And you say, you know what? I think I can do that in about 5 minutes. Next, we also talked about chemical changes and physical changes, and we did some demonstrations in class. All right. For example, a chemical change. How do you know a chemical change is taking place? Didn't we mention that burning was always a chemical change? Remember that? We also said that usually some new products are formed. I had put some baking soda and vinegar together. Remember that? And a gas was formed. I didn't start with any gases. And so that was evidence that a reaction had taken place, a chemical change. What about changes from solid liquid to gas? What about changes from solid liquid to gas? I think I need all your attention, okay? This is your first big test in here. What do you think? What about that? If you change from a solid liquid to a gas or a gas to liquid to solid, what's that? What kind of change is that? Physical, because the chemical itself did not change, did it? Okay, so we talked about that. We did Alka-Seltzer, the bubbles that were formed. Okay, did you ever think about what kind of bubbles there were? What do you think those bubbles are made of? Anybody have an idea what the bubbles are made of? It's carbon dioxide. I'm going to show you a couple other things like that. So here are some examples of some physical changes and chemical changes. And we did these in class. I don't know if I burned paper, but we did evaporate alcohol. We also burned alcohol. We had the big blue bottle. We did that. Ice melting, physical change. All right. What if you just mix something? What if you just mix something like salt in water or BTB in water? What kind of change is that, you think? It is physical. It's physical because if I put salt in water, is the salt still there? Yes, and the water's still there. Nobody's changed. Okay, so mixing does not mean a chemical reaction. Let's go on. We did the baking soda and vinegar. Baking soda and vinegar. And what we did know about that gas, what do we know about that gas? We couldn't see it, but what kind of properties do we have? Vinegar has a smell, but the gas that came out didn't. But remember, I asked somebody to come here to help me, and what happened when I didn't pour any liquid. I had baking soda and vinegar in a big flask, and then I had a candle burning, and what happened? The gas had the property of what? Did it support burning or did it put out a flame? Did it support burning? It made it burn more? I thought it put out the flame. Didn't it? So chemically, it puts out flames. What is a physical property of the gas? What happened? Why did it come out of the bottle? It was what? Say it again. Dense. More dense than what? More dense than air. That's a physical property, isn't it? All right. I thought I'd show you one more that goes along with that, and it has to do with what I'm going to do next. So I need a volunteer. Come over here. And who wants to volunteer? All right, come on. Thank you. Now, what I'd ask you to do is just a brand new straw, so that you can take the paper off. And I'm going to put some BTB in here. We have some BTB in the water. explain to you what BTB is. It's bromothymol blue, but what does it do? And I'm going to show you something here. Now, when you breathe in, I'm going to take every mask you put out. When you breathe in here, make sure your first breath is not big, or else it'll go all over you. So just kind of start off, just keep bubbling it, keep bubbling in there. So let's watch what happens when she breathes into the straw. Don't drink it. You're going to put your breath into the water. So you're going to breathe into it. Everybody watch. So BTB is a special kind of a chemical. Go ahead, you're all right.
Like blow and stuff?
Yeah, when you first start, blow near the top of the water and then make it go down lower, okay? Because if you start at the bottom, it'll kind of all come out at you. I try to make sure not to put too much in there. You'll be all right. There you go. You blow, going down, make bubbles. Make some bubbles. Make a lot of bubbles. No, you actually, that's a brand new straw, so you can put it on your mouth.
Oh, okay.
Yeah. There we go. There we go. Now face everybody so they can see if anything's happening. And just keep doing that for about 30 seconds. All right. Keep going. Now she's got it. Now she's got it. Do you think anything's going to happen here?
Chemical change.
The blue changed to a greenish yellow, didn't it? All right. And that's plenty. You can leave that in there. Just put it on there. So something is coming from her breath that changes BTB. You get that? What do you think? And maybe it is carbon dioxide. Let's take a look here. I'm going to put some BTB in here. What we have here, it's called a stir station, and there's a little motor in here, and that motor is connected to a magnet underneath here, and so it gets the magnet to spin. This is also a magnet. See that? So when I put that in there, then I can do this. See, if you become a science teacher, you can do this too. So what I'm going to do is, this is going to actually set up a little vortex. And it's going to mix things, it's going to stir. Everybody see that? Everybody see that? So it's stirring things for me, right? Now, something came from your breath that changed BTB, didn't it? And we also know that when you put Alka-Seltzer in water, what happens there? What's happening now? Now, you can't, everybody see the bubbles? All right. So it is producing bubbles. But the stir bar is making all the bubbles go here. It's producing bubbles, but the stir bar is making them into a tight little vortex. See that? So the gas that came, I never explained to you, the gas that came from Alka-Seltzer, guess what it is? It's carbon dioxide. And her breath is also. Now, I'm going to tell you about BTB. And we're going to go up here to the screen. I have this little petri dish here, this glass petri dish. We're going to do a little series of experiments here. Number one, I'm going to put some BTB down here. And notice that it is, I'll do it in a beaker. Let's put some BTB in here. And a little bit of water. Let's see, which one's water? Water. All right, everybody see BTB? Now what I'm going to do is I'm going to put in here something that I know what it is. And I know that this right here is an acid. Now later in the year, I'll show you how to name these. This is called hydrochloric acid, and I know it's an acid. So let's watch what happens. All right, what's happening? So BTB is called a pH indicator. And if it is an acid, it's yellow. It'll turn to yellow. And what happened over there, and Larissa breathed into that, it's not that she had acid coming out of her mouth, but she had carbon dioxide, and it combined with water to make an acid called carbonic acid. So she was able to make carbonic acid by breathing in there. And how did I know that? That would have been a boring experiment without the BTB. It would just stay the same color, right? Clear? But the BTB says you're making an acid. And what about the Alka-Seltzer? Those bubbles, what are they doing? They were making a what? They were making a what? Acid. And those bubbles are carbon dioxide. They were also making carbonic acid. All right, so anyway, we know that in an acid, BTB changes from blue to yellow. So when you were doing your experiment, every time you saw BTB change from blue to yellow, and I will tell you there's an intermediate called green. It might go, if it just slightly changes, it'll go blue to green. And then it'll go green to yellow. Get that? But anytime it goes from blue to green or blue to yellow, it means you're causing the pH to go down as an acid. Now, something that's kind of interesting about this is that, okay, I think this is the right one. Let me put this in here. Whoops, wait a minute. This one. Let me put this in here. What a lot of people don't understand is that these indicators, they don't disappear. They actually just change colors. So I put base in here, I put some sodium hydroxide in here, and it went back to blue. And if I put more acid, I don't want to waste my acid, if I put a lot more acid in there, it'll change back to yellow. Yeah.
Is blue an indicator of alkaline?
So what happens is, when I buy this, it actually comes out green. It comes out to be neutral. But I don't want people asking me, why do you call it BTB when it's kind of like greenish? So I make it look a little more blue. You get that? And then it'll change from blue usually to about yellow. Are you okay with this? This is called an indicator, yes.
Is that a chemical change or physical change?
Oh, an excellent question. Excellent question. It's not as easy as you think, because there is a slight change in the BTB. There is a slight change in the way the atoms are arranged, and it makes it give off a yellow color versus a blue. So I'm going to call it a chemical change. So I'm going to say yes. What an excellent question. Indicators are interesting in that they indicate something that's happening. All right, let's try another one now. Let's try, I have some vinegar. Vinegar. I wonder what vinegar is. I'll put some vinegar on here. What do you see? What did BTB do? What happened to BTB there? So what do you think's in vinegar? And if you look on the bottle, it says contains 5% acidity. Matter of fact, the acid is called acetic acid. It contains 5% acid and 95% water. That's what you're paying for when you buy vinegar. 95% what you pay for is water. 5% is what gives your tongue that little tang twings. You know, pickle juice is mainly vinegar. That's why it kind of makes your tongue like tart, right? A little tart. Ketchup, mustard, taco sauce. They all have that in there, don't they? They're all acids. All of them are acids. All right, so I want to show you the next round here with indicators. Let's take a look and tell me where I'm at here. So BTB, if it's in an acid, it's yellow. Do you want to stay in here? You okay staying in here today? Huh? You want to stay, right? Okay. Look down where I'm at now. It says BTB indicators. If it's in an acid, it's what color?
Yeah.
And what if it's in a base? It's blue. And green is just something like in between, kind of neutral, all right? But then I had these other ones. Didn't we use this paper in the experiment? Okay, let's take a look. And so we had 3 kinds of paper in the experiment. Let's take a look at those. What's that called? What are these called?
Litmus ring.
All right, so two of them are litmus. This is called red litmus and blue litmus, and this is called pH paper. So I think what I'll do is, let me take, here's a drop of acid. Let's do acid. Here's some acid right here. Okay. Now, it doesn't look like acid because it looks like water, doesn't it? But indicators can tell me, they can indicate that's not really water. All right, what is the reaction of red litmus paper to acid? There we go. What happens?
Capillary rejection.
It just stays red, doesn't it? Didn't it? It looks darker because it got wet. What about this? Ooh. So when you're doing your experiment, I didn't tell you what it meant, but now you know every time blue changed to red, it indicates what? So I have a memory trick for you, okay? And I'm not swearing either. Ready? I sound like I'm from Texas. If blue changes to red, acid. Okay. Anyway, so that's my memory trick. Blue to red, acid. Yep, can you remember that? So what if blue to red means acid, what would red litmus paper do in acid?
Stay red.
Stay red. Okay. Now, let's do another one. Let's do a base. This is a base, sodium hydroxide. Oh, don't mix. There you go. Here we go. Let's do blue litmus paper in a base. What does it do now? It's nothing. Just gets wet, doesn't it? And what about this one? Ooh. So when you did your experiment, anytime red changed to blue, it meant a base, didn't it? So how do you memorize this, okay? Blue to red. So what's the opposite of that? See? Now you have it. Now you know about litmus paper. Did you know you can buy litmus paper in a paper form? You must. Did you know you can buy litmus in a form of a powder? Do you know some magicians do that? A magician can get litmus in a powder, and they can say, I want to pour some water in this glass. It's not really water. It might be an acid. And so if he has, let's say he has something like, what if he had something that looked kind of like blue? He thought it was blue drink, and he put some more drink in there, and it changed to red. Well, he was using an acid, wasn't he? And there are all kinds of indicators that magicians can buy. I want to show you one more, and then here we go. The pH paper is interesting in that what's going to happen here? I'm going to put that in the acid. And what do you see happen there? Wow, and it got red, but it got really red, didn't it? And then what happens when I put it in a base? And whoa. Now, what's interesting about this, though, I thought I had it with me. A little tube, not this big. Here it is. All right, everybody look at this. When you do pH paper, litmus can only either stay the same color or change. That's all it can do. Red can go to blue or it can stay red. What can blue do? Change to red or stay blue. You get it? That's all it can do. But what can pH paper do? It can change all these colors. All of them. And how's that? And so what happens is, in the pH scale, look at your handouts here at the bottom. Did you guys do anything with pH in middle school? Okay, so pH tells you about if something's an acid or a base, and a little bit about how concentrated it is, kind of like that, okay? So, does everybody know what the pH scale goes from what to what number to what number? Down here, look at the bottom. It goes from 0 to 14. And guess what's right in the middle? So if you had a pH of 7, that would not be an acid, it would not be a base, you would be neutral, wouldn't you? You'd be neutral. Now here's my memory trick for this. What letter comes first, A or B? So the acids are the low pH numbers, and the bases are the high pH numbers. You get it? A, B. So if you have a pH of 0 or 1 or 2 or 3 or 4 or 5 or 6, what are you? And what if you are 8, 9, 10, 11, 12, 13, 14? See? And so this litmus can tell me you're an acid or you're a base, but it can't tell me how concentrated. A pH of 1 is really concentrated. A pH of 14 is really concentrated as a base. Now, I'll talk a little bit more about it during the year. All right, so do you have any questions on that? The memory trick, blue to red, acid, that's pretty good. Now, let's flip it over. And I want to show you one more demonstration over here. Okay. Now, this is actually what's found on pH paper. And if you look at the ingredients, it has 1, 2, 3, 4, 5. It has not one indicator, not two, but 5 indicators. And each indicator can change either 1 or 2 or sometimes 3 colors. And that's why I need that little chart to tell me about it. So one of these indicators only changes from like 0 to 2 pH. Another one might be 2 to 4. And so what I'm going to do is put some of this in here. Now right now it's close to neutral. It's kind of like in the middle of the pH scale. So I think what I'm going to do is run it all the way up to 14. How do I do that? How am I going to run it up to 14? What do you think I should add? What is it? Somebody said it? A base. So let me go get some base here. Oh, I dropped the base. Wait a minute. You not smiling?
What?
So what I'm going to do is, not too fast. Sometimes when I stir, if I stir it too fast, it does that little nervous, so I need to go in circles. So now it's slowing down. Yeah. So right now, it doesn't like, the bottom of that container. The bottom of this container is kind of roundish. But I thought it was big enough so you could see it. I hope it's gonna work. Come on. Stir. Alright, so what we're gonna do is, I'll just put a little bit of this in here, a little bit of base, and let me let it stir for a little bit. So on a pH scale, this is a little bit sort of like neutral, so I'm gonna jack it all the way up to maybe about 13 or 14, and it's gonna really be a base. That's kind of pretty. It's a little bit dark, isn't it? But can you see the color or not? Okay, so now, I'll start with something that is not a great acid. Carbonic acid is not a great acid, but I might be able to produce enough carbonic acid to neutralize. If I could neutralize the base, the pH will start going down and down and down and down and down. And maybe we'll see several colors, okay? Let's try. See the purple? Also, the indicator is fun because I can also tell what's going on. Look where that tablet is. You see any colors around the tablet? A little bit lighter, right? But then it mixes with everything else.
Oh, it's getting yellowed out.
What?
Green.
See, it's mixing now and neutralizing more. And as you add more acid, it's neutralizing more of the base. Let me go a little, did I put on? Go a little faster. Oh.
Orange.
Wait, oh.
I called it.
But we know you're getting there the red, orange and red, you're getting down the acids though, aren't you? And see, this is still base, see? This hasn't mixed yet, but it's getting there, neutralized. Put a little tornado in there, then. Now, do you want me to change it, like, really?
Yeah.
What would I use to get it?
More acid.
And vinegar is okay, but it's not a great acid. This is actually hydrochloric acid, and this one you don't know what 2 molar means, but it's fairly concentrated. So I should be able to change this way past green. Okay, what do you think?
Yeah. I'll get it.
Yeah, it's pretty good, huh? Wait. So I wanted to introduce that to you because BTB is an indicator. And tell me again what the colors are. three colors. So blue for base and yellow for acid, and green's kind of in between, right? How about litmus? Blue to red,
That's acid.
acid,
Oh.
and then red to blue,
Base.
base, okay? And then this right here, the pH paper has 5 different indicators in it, and it's, when I get it as a liquid, it's called universal indicator. And it can do all kinds of things, so that's kind of neat. All right. So now let's take a look, and we're almost finished. Actually, I want to have a little bit of time. We can sit in groups maybe. Skip this for a minute. I will tell you on the test, I do have a picture of the candle. And it'll say, label the different zones. There are 3 zones of a candle flame. Remember that? That's going to be easy?
Yep.
Well, tell me the 3 zones.
Reaction zone.
Yes, where's that at?
It's the
Right, it's blue, right?
it's the
So,
limit.
all right, what else?
And then you have the dark zone and the limit.
That's, okay. And then what? Yes. And then I am going to ask you the temperatures. And what I would do is, remember the wick itself is what? 600? Right above the wick? 800. And at the top of the dark zone? It's getting hotter. It's by 200s, right? 600, 800, 1,000. In the luminous zone, 1,200. And then at the top of the reaction zone, somewhere right around here, 1,400. Okay? This is pretty nice for me to tell you what's on the test. So I'm hoping you're going to use this. Anyway, if you read through here, it tells you what's going on in each zone, and we read that in the article. And remember we used the term complete and incomplete combustion, remember that? And so what kind of a flame is, what kind of flames are there? What are the 2 kinds of flames are there? I don't know if I put that on there or not. I have it on my list here, but what are the 2 kinds of flames? Well, one of them is called a what? Pre-mixed. So pre-mixed flames, I mean, I'll change that in a minute. A pre-mixed flame is one that the fuel has already been mixed with air and it's got plenty of oxygen. You get that? And so if you're ready to do a chemical reaction, don't worry about it. We're going to be okay. And about probably almost 100% of the fuel is going to be burned, right? And normally, what kind of a flame would you get in a pre-mixed flame? It's kind of a blue. Okay, sorry. It's going to be blue. And then we had another kind of flame. What was that? And here, I have to rely on molecules just bouncing around. And as I gobble up the oxygen here, I just got to wait till the other ones bounce in, don't I? Anyway, so what usually happens there, pre-mixed flame, I would say almost all of it is called complete combustion. What are the 2 products when you have complete combustion? What things are produced? What is it?
Carbon dioxide.
Yes?
Water.
Yes. Now, in a diffusion-fed flame, usually lots of fuel they don't get enough oxygen, and you end up getting incomplete combustion. And so what are some products there?
Carbon dioxide.
And water, but what else?
Carbon dioxide.
And what is this stuff right here? C and C2, what do we call that?
Carbon and
That's carbon, also known as soot, right? Isn't that what this is? Okay, just a minute. Hello. Okay, thanks. Cardi, you're going somewhere. All I'm going to do is have them get in groups and write a story using these words.
Can I take a picture of that top part?
Yeah. We had that yesterday, but there you go. So we get this stuff called soot, and also we get this thing not so nice. What's that not so nice stuff that's produced?
Carbon dioxide.
Not
Carbon monoxide.
carbon monoxide. That's even worse. Okay. So that's part of the story too, isn't it? Also at the bottom, and then I'll let you get in groups here in a minute. I also did some demonstrations with Michael Faraday, didn't we?
Yeah.
What if I ask you about when did Michael Faraday do his work? What if I say 1650, 1750, 1850s, 1950s, 2050s?
Is it,
What do you think?
1850?
All right. Even though he gave his Christmas lectures to kids in 1860, he did a lot of experiments probably around 1850, that kind of thing. What else you know remember about Faraday? Why was I said he changed the world, and I even did some demonstrations. I still have them right here. I have some of them sitting right here. What do you remember? Yeah, the connection between what?
Electricity
And-
magnetism.
Right, and so what happens if you have a magnetic field and you run wires through it? You can generate what? And that's called a generator, isn't it? But what if I already have this little thing and I put electricity into it? What can I do? What do you call it? A motor. Very, very good. And it did change the world because the whole world produced electricity with generators, doesn't it? So he did all this other stuff. And remember the story? He stopped going to school at 13. He worked as a bookbinder for about 7 years. He didn't get paid very much for that. What a fortunate thing for him to have Humphrey Davies hire him as an assistant. And then he eventually became the head of the Royal Institute, that kind of thing. All right. Now, what I'm going to do, what I'd like you to do the rest of the period is, I ran out of time yesterday, so I'd like to give you the rest of the time to sit as a group. And if you just want to say it out loud, you can, but my own advice would be to actually try to write out a story including all these words. And you said, I know how a candle works now. So go ahead and find, let's say 2 or 3 people in a group, and you have the rest of the period to try to turn this into a story of how does a candle work. All right, you have the rest of the period, okay? I'm going to turn this off.